Alright, this is Mr. C again. Today we're talking about inclined planes, and we need to calculate some of these simple machines problems using inclined planes. So here's another example for you to look at. The problem that I'm faced with, an engineer is given the task of designing a ramp that will be used to transport pallets to the top of a loading dock. The height of the dock is 5.5 feet. The average weight of it is 2,300 pounds. The company wants to ensure the safety of their dock workers and wants to ensure that they push or pull no more than 75 pounds of force when they move the pallet up the ramp. Sketch a design of the ramp and calculate the length of the slope. Then I'm given another part. If the company only has 150 feet of clearance between the loading dock and the curb of the street, will they be able to build this ramp? So let me start out here. We'll start out with our loading dock ramp that we're going to design. So we just draw our inclined plane. So now notice this triangle represents my inclined plane, and because we are engineering students, we also need to talk a little bit about drawing protocols. That's my object line. So I'm going to draw my extension lines here, and that we know is the height of the dock, which is 5.5 feet. I'm going to go ahead and convert that to decimal, 5.500 feet, and draw my dimension lines for that dimension. Notice my dimension lines have the arrowheads that I'm going to put on there. So again, we want to also, as engineers, kind of try to follow some fairly good drawing techniques. I also have this distance here, which is my run. We don't really know what that is just yet, so we'll draw the dimension lines in. We're not quite there with those yet. And of course I also have my slope, or this dimension going from here to there, and I'm not sure what that is, but I do need to calculate and figure out what that's going to be, because it asked me in the question. So calculate the length of the slope, so I'm going to be finding out what this is as I do my calculations here. And I'm going to leave these open for right now. So as I go over, obviously we're doing these simple machine problems, so we need to do some annotation here. So we got a force of a resistance and a distance of the resistance. We've got the force of our effort and our distance of the effort. And right now, the only one that we've really been given, actually we've been given three of them here. Our force of our resistance. We can go ahead and draw this force right here. So, and that force, this is our F of R, which is 2,300 pounds. So we'll go ahead and put that in here, 2,300 pounds. And the company's requirements that they're wanting to satisfy, they don't want that effort to be any more than 75 pounds. And we also know our DR, the distance of a resistance here, is 5.5 or 5.500. Immediately we need to determine our IMA and our A on this particular problem. And if you remember, we got to choose one of these that we have. Well, we have both our resistance force and our effort force. So that gives us the actual mechanical advantage that we're going to achieve here of 2,300 pounds divided by 75 pounds. Now, remember, I've always said make sure you're keeping track of your units here too, so that way we'll know. In this case, those units cancel out, and I'm going to get my calculator out here, and we'll divide 2,300 by 75, and we end up with 30.667. We'll just round that to 667. That is my actual mechanical advantage on this type of a ramp. Alright, and I need to know now my distance of the effort. So we've got two distance is left. We've already identified this as the run, and of course this is our slope here. And which distance of the effort is going to be, if you think logically about it, what length am I moving that pallet up? Well, we are moving the pallet up the slope, so my distance of the effort here is actually the length of the slope. Yes, it's true, I'm only moving in my horizontal dimension the distance of the run, but I'm actually moving the pallet all the way up that ramp, so that's the total amount of length that I need. So here is my DE. And if you recall from our PowerPoints on Project Lead the Way, slope does equal this, they label this as L, that length over our height. So we've got to figure out some things here for our length over our height. So, or in this case, our DE over our DR, which just so happens to be the same thing as our IMA, our ideal mechanical advantage. And if we are using static equilibrium here, we can then turn around and set IMA equal to AMA. We've already calculated out our AMA to be 30.667, so let me just go ahead and substitute the AMA here, 30.667. And we will say that that equals DE over DR. Well, we know DR, but we don't E, so this equation goes DE over DR, which is 5.5 feet. Alright? Now, all we have to do then to solve for DE is take DE, we'll cross multiply in this equation, and we get 30.667 times 5,000, or times 5.500 feet. I'm sorry, 5.500 feet. Again, I just about messed up because I was reading this, I got a little sloppy. I was reading that as a comma instead of a period, so we do need to try to make sure neatness counts a lot here as we go through. Get my calculator. 0.666 times 5.5 equals, our DE here is 168.667 feet. So that is the amount here as 168.667 feet. Now the last part of this question asks and says that the company only has 150 feet of clearance between the loading dock and the curb of the street. Will they be able to build this ramp? So now we're trying to find out, alright, so this, the maximum that this can be is 150 feet. That's the max. Because if they extend any beyond 150 feet, then they're going to be out into the street and they can't build it and meet the city guidelines. So 150 feet max. Now we need to see if our run does that. And in order to do that, we of course would need to use some trigonometry. We know that this is a right angle, and of course by Pythagorean theorem we can have a squared plus b squared equals c squared is Pythagorean theorem. Now I want you to start to think a little bit like an Pythagorean, make sure I spell this right, Pythagorean theorem. I want you to start to think like an engineer. In this ramp, and we're not really going to label this as a squared or b squared or c squared because that's not really correct for what we have. In engineering, the horizontal surface here, or if we talk about this in terms of a Cartesian plane, horizontal distance is really our x. This height here is really our y, and the length here of the slope, we've already determined that's our L. So we would relabel this as x squared plus y squared equals L squared, so that we keep our terminology and everything correct and uniform. So let me go down here on my paper where I have some space, because we're now looking for x squared plus y squared equals L squared. And that L squared, of course, is my, moving back up here, that is my hypotenuse. So, and this is my x, this is my y. Go ahead and put in what I know right now, basically off of these numbers that I've already calculated. And we're going to hope that we get less than 150 feet. So, x squared is what I don't know, plus y squared is my 5.500 feet. That is squared. And my L here is 168.667 feet. And we're going to square that as well. Alright, so now it's just a matter of x squared. We're going to subtract 5.5 feet squared from both sides of the equation, and I end up with 168.667 feet squared minus 5.500 feet squared. Go ahead and we'll do this out. X squared equals, take this times the square root. Well, that ends up being 168.667 feet in 28,448.444 minus 5.5 squared, 30.25. Let's go ahead and subtract these to get x squared. 28,448.444 thousandths minus 30.250 thousandths gives us 28,418.194. Now we're going to take the square root of x squared and the square root of 28.418.194. Square root of x squared is x. Let's take the square root here. Is 168.5769. So we can just say 577. Doesn't really matter in this regard. We notice that we're just a little bit smaller than our hypotenuse, but in this calculation, in order to achieve this, it actually ends up being too long, and the inch design would not stand up and pass the city ordinances, because you can't have that ramp going out in the street. So they'd have to go back to the drawing board and try to redo this, or maybe they put in and decide to make this 150 feet and see what degree angle or what total length of slope would be in there, so get that. But so this gives you an example. Again, pull out the information that you have to start with out of the question. If you have both forces, then you can calculate your actual mechanical advantage. If you have both distances, then you can calculate out your ideal mechanical advantages. In this case, we had the actual mechanical advantage, which we were able to calculate out to be 30.667. And then we set that actual mechanical advantage equal to ideal mechanical advantage using static equilibrium to find that the distance of our effort actually equaled 168.667 feet. We went through the second part of the question was to see if that was going to be less than 150 feet theorem to determine where we came up with 168.576, and we determined no, we cannot build this ramp and have it meet the 150 feet of clearance requirement there by the company and the city to build that. So, sorry, engineering buddies, we got to go back to the drawing board and redesign this particular ramp or inclined plane so that we can achieve what the company wants for us on this one. So anyway, that's one sample problem for inclined plane simple machines. Check it out, go back through, watch it a couple times, make sure you know how to set this up and do it for the test. Thanks for watching. Have a good day.